Hello, this is Jack Jackson. Let's talk a little bit more about measuring angles. Hopefully you watched this last video that we had down here on trigonometry measuring lengths and angles. And in that we looked at some angles like this. Remember, an angle is the union of two rays with a common endpoint. These technically should probably have arrows on the end to show that they go on forever and make rays. Intuitively, we know that this is a bigger angle than this one, but how do we go about actually measuring that? Okay. And we ran into a couple difficulties. The first one is this: the distance between two geometric figures is the minimum of the distances between between any 2 points on the figure. So in other words, if we have geometric figures lowercase a and lowercase b, then we take the minimum of the distance between points A and B, where A is all the points on A, little a, and big B is any point on little b. So find the point A and the point B so that they're the closest together. Find that distance. That's the distance between the geometric figures. But here we notice that ray AB and ray AC have a common point in A, so the distance between those two rays is 0 every time. Same way here, ray DF and DE, the distance is 0. So that is absolutely no good for measuring. So then we say, okay, how about we find 2 points on the rays in measuring? Well, that's problematic too because, for example, this one is longer here than the one here. So we want to try to get maybe a different way to do that. And we've discovered that what we need to do is standardize that by saying going out a distance of 1 and make a circle of radius 1 centered at the vertex in both cases, and then finding the 2 points where they meet the two rays, for example, G and H here and IJ here, and measure those lengths, the length of that line segment GH and that's line segment IJ, or the distance GH and IJ, and compare those. And that works just great because the bigger that distance, the longer that line segment, the bigger the angle. That works great. But we actually choose to do it a slightly different way. Instead of measuring that line segment distance, we measure this arc length. So this little red arc length from H to G following that circle. So if we could take a piece of string along there and then take that and then straighten it out and measure it without stretching it or compressing it, that would give us the arc length. Or better yet, just take a bendable ruler, i.e. a tape measure, and follow that path and measure it. And that would be the measure of that angle. In fact, that's what we call the radian measure of the angle, which is the natural way of measuring that. An alternate way to do that is go out any circle, not necessarily at distance 1, measure that arc length with your ruler, but then also measure the radius, divide the arc length by the radius, and then you get the radian measure. Notice that your arc length and your radius are both would be measured in the same units, say millimeters or centimeters or inches or something. And when you divide that out, millimeters divided by millimeters will cancel out, and we get a unitless measure. So radians are actually a unitless measure. So if we say an angle measures 2, that means 2 radians, not 2 degrees or some other unit. Okay, so if you tell me something measures, 30, it can't happen because measures have to be smaller than that. We'll talk about here right now. So what possible measures of the angles could we get? Well, the smallest we could get is if we had a 0 angle. If G was right here on top of H, we only had one ray twice. That there would be nothing there to measure. That's going to be a measure of 0. The biggest we could get is if G is pointing exactly opposite direction from H. So it is a straight angle, or in other words, just a line. In that case, this red arc, would be a full semicircle, a half of a circle. And how long would that be? Well, remember that the circumference of a circle, and if you take it and divide it by the diameter, you always get that same number every time, doesn't matter how big or small the circle is. And that number we call pi. So pi is defined to be the circumference of a circle divided by the diameter. So the circumference is pi times the diameter, or 2 pi times the radius. Well, we only want half of that, so it's just pi times the radius is going to be that length of arc length for a semicircle. But wait a minute, we want the radius of 1, so that maximum length across here is pi. So angles then are going to be measured from 0 to pi. If it's a straight angle, it's pi. Zero angle is 0. Proper angles will be strictly between those two. So all angles measure in this interval here. Proper angles are strictly in that open interval. Okay. Now later on, we'll extend the concept of angle measure to encompass measures of a rotation, but these are rotations or rotational angles will end up having numbers that can measures that can take on any real number of radians. You should probably be already familiar with this concept from your trigonometry and calculus classes, or maybe even your high school geometry classes. But for now, we're using measuring angles, which is a type of geometric figure, using radians with all angles having measures in the interval from 0 to pi inclusive, and proper angles in between 0 and pi exclusive. So here's a task for you. Take an angle, any angle that you want, draw it out on a piece of paper using a straight edge, and then only use a tape measure and a compass, measure the radian measure of that angle. So see if you can do that based on what we've just talked about. I'm going to give you a chance to do that and then come back. Press pause now. So hopefully you tried one of these, and there are a couple things that may have been some technical difficulties. In theory, it's not too bad. What first thing we have to do is to make a circular arc. Well, if you have a compass, that's pretty easy. Put the pointy end a B, and then the drawing end out somewhere, and make an arc, and then it will come out here and hit the graph in a couple of different places. Then take your tape measure, follow that arc and measure it, and then finally divide it by that radius, which you also need to measure. Now, the first part's pretty easy. Keeping the path to the thing and bending it on there is pretty easy to do approximately, but it's pretty hard to keep it right on the path enough to measure that with any accuracy for detail. Finally, the final step is you have to divide the arc length by the radius. It's going to be a lot easier if you're dividing by something like 10 units or 2 units, or better yet, just 1 unit, although 1 unit might be too small for practical purposes. It would be nice if we had a pre-bent ruler based on where the scale on the ruler was the same as a scale of the radius being 1, and then we could measure these angles that way. And that's exactly what's a device is called a protractor, a radian protractor. So here it is. So notice that this scale from 0 to 1 here, I want you to convince yourself that if you took a string that long and then bent that string or bent that ruler, it would go from 0 to 1 on this scale as well. And notice this one is set up, so here's 1 radian, 2 radians, 3 radians. And the way you use this is you put the vertex, put this device right on the vertex there at 0, and the initial ray going through 0 here, and then the terminal ray will be, or the other ray can be measured off this scale. Notice the darker lines here going up by 0.1s, the little ones are going by 0.02. Using something like this, you should probably be able to measure to the nearest hundredth of a radian. Here's another one where the markings are marked off in multiples of pi over 60 for the little markings, multiples of pi over 12 for the full darker ones that are going to the middle. Now you could cut these out if you print them on a piece of transparency paper or even just real thin paper, and you might be able to use them. But here's what I suggest you do. In fact, it's required for my class. We use a protractor that's actually commercially available, and I don't normally, endorse particular models, but the Pro Radian brand I am going to endorse, and there's the internet web address there for it. And they have this one here. It's called a Pro Radian 2, and it's made out of some nice quality plastic. And notice you can see markings at multiples of pi over 24. That's going to be pretty good for doing a lot of your standard ones. Here's one marked off in multiples of 0.1 radians. And this one's even better because this was marked off in 0.01 radians. So using this one, you can measure an angle in radians to the nearest hundredth of a radian. So what I require my students to do is to buy a Pro Radian Pro and a ProRadian 2 from this ProRadian website. I was able to get mine maybe a couple years ago sent to me, just ordering those two things, along with shipping and taxes and everything. It was less than $11. It might have gone up, but it should be not too far off of that. So notice that when you measure in radians, you have a nice simple relationship between the theta, which is the measure of the radian measure of the angle, and the s, which is the arc length, and r is the radius. Theta is just s over r. And the formulas that in calculus really only work out nicely when you do things in radians. So for example, you might know from a calculus class that the derivative of sine x equals cosine x. If you don't know that, that's not necessary for what we're doing now. But I just want to point out that that only works if x is measured in radians.